Let's sketch some Venn diagrams and use shading to represent these individual sets. So when we're trying to figure out what something looks like, if we want to say this is A intersect B, well, I'm going to draw up just a generic Venn diagram here with sets A and B, and I want to shade in the region that represents, the region or regions that represent the intersection of these two. This is a pretty simple example. This is just the region that's in common with A and B. So it would end up looking like this. If this is what it looks like if we were only doing a Venn diagram with 2 sets. If we were doing a Venn diagram with 3 sets, A, B, and C, this is going to look the same, well, similar, except you'll notice that when I shade this in, I go right over the top of C. I essentially am ignoring the fact that this line with C exists, because ultimately it kind of doesn't really have any impact on A intersect B. In order to be in A intersect B, you have to be in both A and B. It doesn't say anything about C. It doesn't say you should be in or outside of C. So the intersection here would look like this. All right, let's look to see what these A union C would look like. If we're just drawing a Venn diagram with 2 sets, well, A union C, this is going to be everything that's in A, and then you're going to tack on anything that's in C that wasn't already gotten. So union looks like this. Now, if you're tempted to say that this is everything, well, be careful. It's not, because remember, there could be elements that are out here. This area is not shaded. And if I did a Venn diagram with 3 sets, let's call this A, B, and C, well, again, I'll start off with all of A, and C is the set down here, so I'll tack on all of the rest of C that wasn't already gotten. And this is what the shading looks like there. Again, I'm kind of ignoring the fact that B even existed, because it wasn't part of this at all. Now, those are kind of simple examples because there's only one operation that takes place. The moment you start having more operations take place and you're trying to graph these things, you have to get a little bit more careful about how you're doing things. So what I'm going to do is I'm going to draw up a Venn diagram here, and I'm going to label my regions. I'm going to call this 1, 2, 3, 4. So just to talk about them, things that are in this region versus in that region, and so on. So A, you could think of them as regions, or actually I'm going to treat them as individual elements within the region. A consists of regions 2 and 3, rather. B consists of regions 3 and 4. Well, then I can do A complement. Oh, and I guess I should also say U is regions 1, 2, 3, and 4. So by doing it this way, I can essentially use all of the techniques that you've already learned on how to do unions and intersections and all of that stuff without having to try to visualize it. You can just use that stuff here, and then you can shade in the appropriate stuff afterward. So let's see, A complement is going to be regions 1 and 4. Graphically, if you think about what that means, this is A, the stuff that's inside A is right here. A complement is everything that's outside of A. That's going to be 1 and 4, these two regions right here. That makes sense. If I was to shade this in, A complement would look like this. You can see it's everything except A, but of course I don't want to shade that in. Oops. Okay. So now I want to do A complement intersect B. Well, let's see. A complement was 1 and 4. B was 3 and 4. The only thing that's in common between those is region 4. A complement intersect B is going to be just region 4. So that would be this crescent moon shaped region right here. And you could use the same sort of thing for getting more complicated. So if you have 3 sets, I just want to make sure I can draw everything where I can label all of my individual regions, A, B, C. Let's call this 1. And when I label my regions, I try to be fairly consistent so that I can kind of reconstruct it if I need to. You can see I'm just going from top to bottom, left to right. Alright, so first off I'm going to figure out what A union C is. A is regions 2, 3, 5, and 6. C is regions 5, 6, 7, 8. If I'm taking their union, that means I can start off with 2, 3, 5, and 6. Start off with all of A, and then tack on anything from C that was missed, so 7 and 8. Now, I want to do I want to take B and intersect it with this mess. Well, B is regions 3, 4, 6, and 7, and the only ones that are in common here, well, actually it looks like 3 is in common, 6 is in common, and 7 is in common. 3, 6, 7. So that means B intersect A union C is going to be regions 3, 6, and 7. This one is still within the realm of possibility of being able to do this without going to, a representation like this, but it gets difficult and really easy to make mistakes if you don't. So I do recommend going and just talking about the region numbers here. All right, let's do this. One more example here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's a 6. First off, A union C complement. So there are shorthands you can think of. A is, of course, everything within A, B, C. C complement is everything that's not within C. So A, let's see, we're starting with a union, so I'll just write down the numbers. 2, 3, 5, 6. And then we're going to take on anything that was not in C that hasn't been gotten already. Well, let's see, we haven't gotten 1 and 4, and those are both outside of C, so I'll tack those on. Both 7 and 8 are within C, so those would not be included. All right, and then I want to take B, intersect that mess. Well, let's see. We have 3, 4, 6, 7. Let's see which of those are included. 3, 4, 6. Because again, B is 3, 4, 6, and 7. We're looking for the intersection of the two. So I'm actually starting with B here, and then kind of looking to see what's here. So 3 is there, 4 is there, 6 is there, but 7 is not. So you'll notice 7 is not in the intersection.